This situation where we have a tank and salt water is being mixed in the tank is a very famous kind of situation where people learn how to do some basic modeling with differential equations. The official name of it sounds kind of fancy. It's called compartmental analysis, but tank mixing salt water, I just prefer thinking of it that way. And there are assumptions that go behind what's going on here. We're assuming that the salt water mixes instantaneously throughout the entire tank. Of course, that doesn't really happen in reality. There are spatial and time effects. The salt can't mix instantaneously. Now, you can kind of pretend it does because you've got these blades that are spinning really rapidly that are mixing things up as rapidly as possible. And if that's true, that makes your model as good as can possibly be if you don't want to go to partial differential equations, which we definitely don't want to right now. Partial differential equations are much harder than ordinary differential equations. And we can't understand partial differential equations without understanding ordinary differential equations. So again, the setting is you got this 100-liter tank that's got 20 liters of pure water at time zero. At time zero, salt water with a concentration, say, of 5 grams per liter is flowing in at a rate of 7 liters per minute. You also have a drain where the flow rate is 5 liters per minute, and it's got an unknown concentration. In fact, that's the hard part, is the concentration is changing. That's why you need a differential equation to ultimately model the amount of salt in the tank in grams as a function of time, not in seconds, but in minutes. Okay. And if we know the amount of salt, we could also figure out the concentration of salt too, right? Divide by the volume. The basic principle that you need here is that the rate of change of the amount of salt with respect to time is rate in minus rate out. Rate in minus rate out. There's salt coming in, there's salt going out. And to figure out these rates, it's really, really helpful to think about units. In Calculus 1 that I'm teaching right now, we're talking a lot about Leibniz notation, dq dt in this case, emphasizing that the units for the derivative are the units of the variable in the numerator per unit of the variable in the denominator. So this would be in grams per minute, not liters per minute, but grams per minute, because we're talking about the salt, not the fluid itself with this differential equation. So whatever rate in and rate out are, whatever those things are, they have to have units of grams per liter. Oh, if I multiply those two things, the liters will cancel and give me, did I say grams per liter? Grams per minute. They have to have units of grams per minute. If I multiply these two things, the liters cancel, giving you grams per minute. Yeah, if you multiply the concentration by the flow rate, 5 grams per liter times 7 liters per minute, the liters cancel. This is 35 grams per minute. But what about the rate out? The flow rate is constant, 5 liters per minute, but the concentration is not. Something grams per liter times 5 liters per minute. Well, liters will still cancel, giving you grams per minute. But what goes here and what goes there? Liters is a volume. So in the bottom, you want the volume, right? But what is the volume? It's changing. Starts out at 20. I guess it goes up by 7 minus 5, 2 liters every minute, right? The volume is increasing by 2 liters every minute. So is it 2t? 20 plus 2t, because you're starting out at 20. If we were starting out empty, then it would be 2t. But there's 20 liters of fluid in there to begin with, so we have 20 plus 2t. But what about the grams? That's just Q. Should I write it as a plain old Q, or should I write it as a Q of t? It's best to write it as a Q to be consistent with what we've done with differential equations. Usually, so far, we've used y as the dependent variable, and we've written dy dt equals then something like 2t plus 5y or something. Realizing that y is a function of t, but we don't write the y of t on the right-hand side. You just write a y. Yes, there's a t in there, but it's not next to the y. It's not a y of t. Could be a y times t, but it's not a y of t. Likewise, don't put q of t here, just put a q. So this simplifies a little bit. dq dt is 35 minus 5q over 20 plus 2t. And this thing is my f function as a function of t and q. Of course, it would be a function of t and y if I used y instead of q. That's the differential equation. The initial condition for the amount of salt is that there's no salt, q of 0 equals 0. So there's your IVP. You're going to be learning, if you're up with things over the weekend, how to solve this IVP. I'm not going to tell you in class today, other than to say the method you use is not the same thing as before with the undetermined coefficients. Instead of a new method called the method of integrating factors is what's to use here. But let's have Mathematica solve it for us. So I'm going to go ahead and do it this way. I'm going to go ahead, also for the sake of making a slope field, define a right-hand side function like that. And again, when you define functions in Mathematica, you've got to use underscores after the variable names when you first define it, but then after that, don't use underscores. It's the right-hand side function. It's the 35 minus this fraction. I can hit this fraction button here. 5q, oops, not 5 over q, 5q over 20 plus 2t. Enter it with shift return. I can make a slope field without solving the differential equation. Vector plot. With slope fields, you make a 1 first, then the right-hand side function. The independent variable t goes from, say, 0 to, I don't know, well, when is the tank going to fill up? It starts with 20 liters, and it's a 100-liter tank. It's got 80 liters to go. The amount of liquid's going up by 2 liters every minute. 40 minutes is how long it's going to take to fill up. Let's let t go from 0 to 40. And let q go from 0 to, if it were 5 grams per liter for the entire 100 liters, that'd be 500 grams. It won't go that high, but that'll give us a picture with the slope field with some arrows. I could try to get rid of the arrows, but I'm not going to bother. I'm going to get rid of the frame and add axes. My solution's got to follow the slope field starting at the origin when t is 0, right? Because there's no salt there when t is 0. Looks like it's going to increase. The salt is increasing and head toward some slanted type of asymptote. Some linear function with a positive slope, not an equilibrium solution because it's not constant. It seems like it's heading towards some line that might look about like this. That the amount of salt is going up curved at first, but then closer and closer to a straight line. And probably getting close to 500 by the end. How do you actually solve it? Desolve or desolve value could be used. I like desolve value because it leaves the answer in a nicer form. In curly braces, put your differential equation with primes. Double equal signs. The most common mistake is to think you can use single equal signs. That messes things up. And you can't get it to work if you use single equal signs. F of TQ. But Mathematica needs to know Q depends on T. So we need to put a Q of T in there. For the slope field, we don't want a Q of T in there. That, in a sense, is the best reason for not having the Q of T. and the right-hand side of the differential equation is so that when you make the slope field, it's done correctly. But with the differential equation, you need to emphasize to Mathematica that Q depends on T, so I do that. Outside the curly braces, put the function you're trying to solve for, and then a comma, and then the independent variable. Sometimes when you enter this, it's not in the nicest form. Okay, is that the nicest form? I don't know. I could try to simplify it. It's kind of complicated, but you can't really simplify it much anyway. I guess that simplifies it a little bit, although I don't know why they factored the, might as well multiply the 10 through that. Percent refers to the preceding output. That's why I'm using a percent sign. That's probably as simple as it's going to get. And do notice that it's a linear function minus some function that as t increases is going to go to 0. Just like I was predicting, heading toward some slanted linear function. And we could use this expression and plug in t equals 40 to predict the amount of salt at time 40. Probably get a numerical approximation to that as well. About 498 grams, so close to 500 by the time the tank fills. It's hard to always know. I usually default to just using simplify, but if it's not seeming to help enough, I use full simplify. Expand will multiply things through, like the 10 gets multiplied through. And again, the percent sign always just refers to whatever the preceding output is, and that's why I'm doing that. This is funny syntax that allows me to plug t equals 40 into the preceding output. And this does the numerical approximation.